Hi everyone, welcome back to another ECChem video. In this video, I'm trying to explain to you some reactions of phenols. Phenols are more reactive than benzene because the electron density in the aryl ring in phenol is higher than in benzene. Therefore, electrophiles can be attracted towards the aryl ring in phenol much easier than benzene. Now this higher electron density comes to phenol molecule because there's a delocalization of lone pairs of electrons happening from oxygen atoms in OH into the aryl ring. How exactly does it happen? You can see in this phenol molecule, there are two lone pairs of electrons. And next to it, we have an aryl ring. Aryl ring has an electron delocalized system. These pi electrons are in a constant delocalization. So if one of these lone pairs of electrons is also going to participate in this electron delocalization, you can get a more stable structure. Therefore, in the initial stage, a lone pair of electron on the oxygen atom gets delocalized towards the ring. See, the arrow shows that. When electrons come towards the first carbon, there is a double bond between first carbon and second carbon. The pi electrons in the double bond get concentrated towards or get pushed towards the second carbon atom. It's given over here. As it happens, the electrons in the pi bond between carbon 1 and carbon 2 get shifted towards the carbon 2 as seen or as shown in this arrow. Okay, that's it. Now what happens? When pi electrons come towards the second carbon atom, its electron density increases and it gets a negative charge. See the negative charge on the second carbon atom. The oxygen has got a positive charge, and there's a new double bond formed between oxygen and ring. A negative charge on carbon is unstable. Therefore, these electrons, which have given a negative charge to the carbon number 2, get distributed towards the third carbon atom, making a double bond, new double bond. And then this double bond, it will get pushed towards the fourth carbon atom, giving a negative charge towards, or rather on the fourth carbon atom. You can see the electron donation from the negatively charged carbon atom towards the third carbon. It will definitely make a double bond. And the double bond electrons get pushed towards the fourth carbon. Now that gives you another structure. See what has happened in that. A new double bond has been formed between carbon number 2 and 3, and the carbon double between carbon 3 and 4 has disappeared. Instead, a negative charge has come to the fourth carbon. What will happen next? As I said before, having a negative charge on a carbon atom is unstable. So these electrons will be donated to the other side, towards the carbon number 5. But when electrons come towards the fifth carbon, there's a double bond. This double bond will get shifted by giving electrons to the fifth carbon over here. And in the next diagram, we will see 6 carbon. Yeah, you can see the negative charge has gone to 6 carbon atom. Positive charge is on the oxygen still. And this is a continuous process. In the last stage, the electrons which give negative charge to the 6th carbon atom get distributed towards the first carbon atom, making a double bond. And as it happens, the oxygen-carbon double bond changes to a single bond by giving the pi electrons towards a positively charged oxygen atom. Now see, you have got the phenol molecule neutral back again. You can see in this phenol molecule, now the middle 3 structures show negative charge on the second carbon, on the fourth carbon. On the other side, 6th carbon, we can call it second carbon also. Therefore, remember, phenol reactions happen on the 2nd place, 4th place, and 6th place in the ring. So we say OH group is 2,4 direct. Pi electrons in the aryl ring move distributing the negative charge in the ring. Due to the negative charges generated at 2,4 carbon atoms, the OH group is a 2,4 direct. Having this in mind, we can discuss some reactions of phenol. In the very first reaction, what I'm trying to do is, okay, I have the phenol molecule on the screen. In the first reaction, actually there are two reactions I'm going to discuss together. Phenol molecules are acidic. It's not a very good acid, but then slightly acidic. You can at times figure it out. You can't find out easily if it's an acid, but still it is acidic. Because it's acidic, it can react with both sodium hydroxide and sodium metal. If it reacts with sodium or sodium hydroxide, the same organic compound is produced. In addition, with sodium, you can see hydrogen gas production. When you add sodium hydroxide, you have water molecules coming out. It's more of an acid-base reaction. And then afterwards, phenol can show another reaction with dilute nitric acid also. If you remember, phenols never react with dilute nitric acid because, not phenol, benzene. Benzene never react with dilute nitric acid because benzene is not very reactive, but phenol is more reactive. Therefore, phenol can react with dilute nitric acid also. And it can give two products. In one product, the second place has reacted, and in the other product, the fourth carbon has reacted. You can see NO2 has been added to the fourth carbon over here and second carbon over here. The first compound is 4-nitrophenol, and the second compound shown here is 2-nitrophenol. This is how you get two compounds when you add dilute nitric acid. However, if you add concentrated nitric acid, then you get only one product. We don't have to have sulfuric acid, 50 to 55 degrees Celsius, nothing. You just add concentrated sulfuric acid, just one product will be formed where all the 2, 4, and 6th places in the benzene ring or aryl ring have reacted with the concentrated nitric acid, and the product you have got here is 2,4,6-trinitrophenol. We can discuss about one more reaction, a simple reaction, and it's about esterification. Normally, esterification reactions occur when a carboxylic acid reacts with an alcohol. But in this case, what reacts with phenol is not a carboxylic acid, it's an acid chloride. Acid chlorides react with phenols very fast. You don't have to have any special condition given an ester molecule. Remember, phenols do not react with carboxylic acids, but they react with acid chloride. So if you are asked to react a carboxylic acid with a phenol, the first thing you have to do is converting the carboxylic acid into an acid chloride. That can be done by using substance like PCl3 and heat, PCl5, thiamine chloride. Likewise, there are several substances available for this. Okay, now here you are looking at some very common basic reactions of phenol. But there are two reactions, special reactions of phenol, which I'm going to discuss over here. The very first one is a reaction of phenol with bromine water. Phenol is able to react with red-brown bromine water to produce a white precipitate. How is that reaction happening? Here we have the phenol molecule. You are adding now red-brown bromine into this. When you add bromine water, you can see phenol has the second carbon, fourth carbon, and sixth carbon activated. So one bromine comes to the second carbon. One bromine comes to the fourth carbon. The third bromine comes to, again, we can call it 2 bromine. Or here I have given 6. When you start counting from one side, this is 2, this is 4, this is 6. So we have 2,4,6 tribromophenol. This 2,4,6 tribromophenol is a white precipitate. See what happens. You are adding bromine water. In the dropper, we can see the red-brown color. But when you add this bromine water into this phenol solution, this colorless solution in the test tube, when you add bromine water, the color disappears immediately because of this reaction happening. So we say red-brown color of bromine disappears quickly. So this is one important reaction of phenol. Color disappears and a white precipitate is formed. This reaction happens very fast. You don't have to give special conditions. It just happens at room temperature and pressure. Now we move on to the next special reaction of phenol, and it is the formation of azodye. Azodye means nitrogen-containing dyes. Phenols can react with diazonium ions. You will see what diazonium ions are when I start the discussion. Phenols can react with diazonium ions to form nitrogen-containing dyes called azodye. I said earlier also, azodye means nitrogen-containing dyes. You can see the color of an azodye. If you want to make this azodye, you have to start with, let's say, benzene. If you start with benzene, there are a few steps until you come to this azodye. We'll see. First, we have the benzene. You have to convert benzene to nitrobenzene at the beginning. The conditions are given here. Benzene is reacted with concentrated H2SO4 and concentrated nitric acid. The temperature, remember, 50 to 55 degrees Celsius. See the product. NO2 group has been attached to the benzene ring. This is nitrobenzene. Now in the second step, nitrobenzene is going to react with tin and concentrated HCl. When you react nitrobenzene with zinc and concentrated hydrochloric acid, a reduction reaction happens where you can see in the next picture, here NO2 has gone to NH2. What has happened? Oxygen gone out and 2 hydrogen have come in. So oxygen removal and hydrogen addition, they are both considered as reduction reactions. So here for the reaction 2, I have written nitrobenzene is reduced with tin metal and concentrated HCl. The story doesn't end here. Now, this phenylamine, this is called phenylamine. Phenylamine molecule is reacted with dilute HCl and sodium nitrite. The temperature has to be maintained at 0 to 10 degrees Celsius. If you write less than 10 degrees Celsius, that's fine. When phenylamine reacts with dilute HCl and sodium nitrite at this low temperature, you get diazonium ion. This is called phenyl diazonium ion. The positive charge comes to the nitrogen atom here. There are 2 nitrogen atoms bonded through a triple bond. And this is a highly unstable molecule. So we have to maintain a temperature as low as 0 to 10 degrees Celsius. We can easily convert these diazonium ion, phenyl diazonium ion, into a phenol molecule. If you heat this system, the diazonium ion, you can heat to 50 to 100 degrees Celsius. I have written here with the dilute acid. If you write water also, it's okay. When phenyl diazonium ion is heated to 50 to 100 degrees Celsius with, let's say with water, that's fine. Phenol is formed. See, reaction number 4 gives phenol. Now what are we doing? We are on our way to make azodyes. And the first point says phenols can react with diazonium ion. Okay, now we have phenol here. Where's the diazonium ion? Diazonium ion is here. Remember, diazonium ion is stable at very low temperatures as low as 0 to 10 degrees Celsius. Now, how are we going to allow this phenol to make this azodine? First, you can make this phenol molecule more reactive by adding sodium hydroxide. If you add sodium hydroxide, this phenol goes to sodium phenate ion. Now, this sodium phenate ion is cooled down to very low temperature. Here we can see in number 5, addition of sodium hydroxide to phenol, it should be phenol, gives sodium phenate and it's cooled down to 0 to 10 degrees Celsius. You know, the reason why we cool it down to 0 to 10 degrees Celsius. We are going to react this phenol with phenyl diazonium. I said phenyl diazonium is stable at 0 to 10 degrees Celsius. If you don't cool down this sodium phenate, if you don't cool down, as soon as the phenyl diazonium ion is added, phenol diazonium ion will disintegrate. It will undergo breaking. You will not have phenyl diazonium ion to react with the sodium phenate. So you have to cool it down. And then cold sodium phenate is then added to phenyl diazonium to form an azodine, which is water soluble. Here, you are adding phenyl diazonium ion to cool sodium phenate. See what happens. Always remember, when this sodium phenate reacts with phenyl diazonium, this phenyl diazonium ion gets attached to the ring in benzene, sodium phenate, at the 4th place. This is to avoid a steric hindrance. There's no problem, you know, if this diazonium ion is going to get attached to this 4th place in sodium phenate, there's no much trouble, you know, no disturbances because of the steric hindrance. However, remember, this N2 is having a positive charge. Because it has a positive charge, we can consider that as an electrophile. So this electrophile is getting electrons from the aryl ring in sodium phenate at the 4th place. It can do this at the 2nd place and 6th place also. But then because already there is some group somewhere there will be you know, hindrances due to space problems. So it goes to the 4th carbon. You can see now this sodium phenate is drawn above, and below there, diazonium ion, phenyl diazonium has attached to it. Now the positive charge is not there. However, we have a problem with this. This structure you are seeing, which is produced in the reaction 6, is colorful. But this colorful substance cannot be used for normal paint varieties. If you want to make a paint which is water insoluble, we have to make this less soluble in water. Now, why is it water soluble? This is water soluble because of this ionic N. This compound, you know, probably you can use it for these food colorings also because it's water soluble. If you want to make it water insoluble, so what you do is, how do you get this sodium into this sodium plus? Because we are adding sodium hydroxide in this step 5. So how are we going to remove this sodium ion? We can add HCl. When you add dilute HCl, you can see the sodium plus goes out and that part has gone to an OH group. Now this last product is more water insoluble. So the first compound over here, the product of the reaction 6 is a dye. The product of reaction 7 is also a dye. But the product of reaction 6 is water soluble, and that of reaction 7 is water insoluble. See, between nitrogen atoms, we have a double bond. If somebody asks why this has a color, it is because of the presence of this double bond between nitrogen atoms in this molecule. So this is one of the most important reactions. You come across this question, this diagram in very many paper 4 question papers. I think we have done most of the reactions of phenol, which is required to learn for your exam. Now we'll attempt some questions. With the knowledge that you have gained, we can find out the answers for this. See, what is the question now? Write the reagents and conditions needed for the reaction A. Draw the structure of the reagents added in the reaction B to form Y. First answer is given. Write the reagents and conditions needed for the reaction A. In the reaction A, what happens? This NH2 goes to N2 plus. Actually, Cl is shown here. Cl is negative, N2 plus. So this is diazonium ion formation. X can be changed to a diazonium ion by adding sodium nitrite. And dilute HCl temperature is less than 10 degrees Celsius. Then draw the structure of the reagent added in the reaction B to form Y. Okay, reaction B. I add in something into this. What is the reagent B structure? Try to figure out a little bit. How do you do this work? You see where this molecule is in the final product. We have CH3 over here, benzene ring, okay, is there. Now this is N2Cl. That part has gone into this benzene ring. So what do you think is a product which has, what do you think is a substance which is being added in the reaction B to make this compound Y? A compound containing benzene ring has been added where there should be CH3 group, OH group, and CH3 group attached to it. You can see the substructure here. The CH3 group is as it is. This OH group is here. The CH3 group is also over here. So it's a pretty simple question. But let's see how the other question is going to be. What must you do now here? Identify the reagent needed to carry out reaction 1. Reaction 1 means this. Next one. Draw the structure of the compound G. Next one. Draw the structure of the product H. I think you will be able to find out the answer within 30 seconds. Give a try, please. Even if you didn't write the final answer, if you were able to figure out what the answer is, that is a very great achievement. We'll see. Identify the reagent needed to carry out reaction 1. What has happened here is a very simple thing. CH3 is there, NH2 is there in F. In the product also, we have CH3, NH2. In addition, what has been added? 2 bromine. So we can add what? A equals bromine. Now we go to 2. Draw the structure of the compound G. What do you think is the structure here? Here. This is an acid chloride. Acid chlorides can react with NH2 group. But in this video, I did not show any reaction of this nature. But if you remember, I told esters can be formed by acid chlorides and phenols. A similar reaction happens here also, but of course here we don't have an amide, we don't have an ester molecule. Here we have an amide molecule. How is it possible? What happens is this. See this chlorine atom? This chlorine atom goes with one of the hydrogen in this NH2 part. So when the chlorine goes with one hydrogen over here as an HCl molecule, this nitrogen will get attached to the carbon over there, making an amide. This is a compound which is going to react. Draw the structure of the compound G. Okay, the product has to be shown. See whether you understand this. CH3 benzene ring NH2. CH3 benzene ring NH2 is not there now. NH is there because I told one hydrogen he will go with this chlorine. And then we have C double bond O CH3. This is an amide molecule. Third one, draw the structure of the product H. Remember this nitrogen NH2. Nitrogen has a lone pair of electron. In AS, Bronsted acid and base lessons, we learn hydrogen acceptor is a base, Bronsted base. This nitrogen has lone pairs of electron. Because of the lone pairs of electron, HCl has H plus. This H plus will come and get attached to NH2 and change it to NH3 plus. Because there's a plus charge, Cl minus also goes to sit next to it. Here. Cl minus is not shown here though. You can see NH2 going to NH3. NH2 has no charge, but NH3 has a charge because this nitrogen in the product contains 4 bonds. 1 bond with the allyl ring, 3 bonds with 3 hydrogen. When nitrogen makes 4 bonds, it gets a positive charge also. If you want to attempt one more question, draw the structure of the product C. What product? Oh, here we have. What is the structure of the product C? We have another question. It should be B. Draw the structure of the product in the following reaction. Spelling mistake is there, just ignore it. Give the product. C. What reagents and conditions are needed for the reaction A and B? Take your time. No. Take about 30, 40 seconds and try to figure out the answer. Okay, we'll start the work. In the part A, this is a phenol part. Phenols react with sodium hydroxide, giving sodium phenate. A. C. This OH changes to O minus Na plus. That is the answer for A. Now B. This one should be B. What's happening here? We have a reagent which is an acid chloride. And here we have phenol molecule. In this phenol molecule, this OH, hydrogen goes out with the chlorine making HCl, and to this oxygen, this carbon is going to get attached. See this. The 3 rings are here. O, oxygen is there here. To this oxygen, this part has been added. You remove chlorine and attach this to the OH part. Here we get the product. That's the answer for part B. And we go to part C, A and B. What is happening in A? In A, we have OH, same thing here, 2 rings, 2 rings. In addition here, we have NO2. Because OH is a ring activator, and if the product you obtain here is just containing 1 NO2, then definitely for CA, we have to use dilute nitric acid. What about B? 2 bromine atoms have been added. Just aqueous bromine. bromine water. Study is a bit, if it's difficult for you. Okay, fine. Guys, that's it for this video. However, thank you very much for learning with BSc Chem.